better? Yeah, perfect.
I'll give you a 25-minute warning.
Grand.
So the forward,
back button.
pointer, and
Oh, sorry. Forward was
forward.
that one. Grand. Perfect. Thank you very much. Cool. So good afternoon, everybody. I'm Rachel. I work with NextMove Software, and I'm going to be talking this afternoon about a method that we recently contributed to RDKit for calculating surface area and volume of sort of molecules, proteins, etc. So just for a little bit of context before I actually start talking about what this method does, I figured it maybe be a good idea to give you an idea of where it came from. So it started off its life as an algorithm presented in a paper by a group predominantly at EMBL for calculating surface area and volume based on a dot surface of a molecule. The implementation that I have been working from came to me from my boss, Roger, who implemented the algorithm in C for use from the command line while he was working at GSK in the late 90s, which was predominantly used for calculating buried surface area of protein ligand complexes alongside programs like GROMACS. So how did this end up on my desk? And as a consequence in the RDKit? Some of you might remember a couple of years ago, oops, giving myself away. I stood up at the UGM in Berlin and gave a talk with a nonsense title about the work we'd been doing during my PhD developing new shape-based similarity measures. As a caveat for any PhD students that are listening to this, I'm in the job I'm in now because of that talk, so this is a really good audience to come and speak to. So once I got to NextMove and Roger got his hands on my thesis, there were some grumblings about the way that my mathematician supervisor had defined the surface area of a molecule. So he very kindly shared the code with me as a potential correction to the way that we had done this in my thesis. He also thought that it might make a useful contribution to the RDKit, because as far as we are aware, previously the only volume calculation that was available was for the van der Waals volume. There wasn't any way of getting out the solvent excluded volume. And also as someone who had worked exclusively with Python during my PhD, which anyone familiar with NextMove will know that wasn't going to last for long, this was an opportunity for me to learn a little bit of C++ as well. So just as a little bit of a recap before I get into the details of what the method we've presented is going to be doing, generally speaking, when we refer to the surface area or the volume of a molecule, we're talking about a set of intersecting spheres of a given radius, usually taken as the van der Waals radii, and then we take the surface area and the volume as the sum over those spheres respectively. The surface area and the related volume that I'm going to be talking about today are the solvent accessible surface area, which we get by rolling a probe sphere representing a solvent of a given radius across the boundary of that molecule. Historically, there have been two sort of approaches to doing this. The first was a method presented by Lee and Richard in the very early 1970s, where they took this set of molecules of van der Waals radii, split it up into sections, and then rolled the probe sphere over the surface of the molecule. Anything that was drawn by that probe sphere was considered accessible and contributed to the area that was returned. A similar, slightly later algorithm by Schreck and Ripley, again, took our set of atoms of intersecting van der Waals spheres and represented them as a set of 92 dots. And then the area that we obtained came from the sum of the dots that weren't occluded by a neighboring atom. The work that I'm going to present today is a variant of the Schreck and Ripley algorithm. So unfortunately, I won't have time to go into the absolute nitty-gritty of what this does, but just to give a bit of an idea, this is the class for returning surface area and volume that we contributed to the 2024-03 release of RDKit. The method is compatible with returning surface area and volume for proteins, ligands, and protein-ligand complexes. The default is that we assume we have a small molecule because we figured that was what was going to be of interest to most of RDKit's user base. The method takes in an RDKit molecule object, a couple of Boolean parameters to tell it whether we are looking at a protein and whether we are looking at a protein-ligand complex or a small molecule ligand on its own, a value for our solvent probe radius, and a depth parameter that controls the number of dots that we use in the surface representing the molecule. So by default, we don't include any hydrogens in these calculations because the relative size is kind of negligible. And you would need to go into the code and turn that off if you wanted to include hydrogens. I'm willing to consider adding that in as a parameter if anyone has any strong objections, but we can debate that later in the pub. And as I mentioned, this is a variant of shrake and root play. So the method is quite aptly named. It does exactly what it says on the tin, and it uses two cubic lattices in the calculation of surface and volume. The first is used to group atoms that are nearby. So we take our set of intersecting spheres of van der Waals radius, and we plot them in a grid where each edge of the cell is 2 times the biggest radius amongst our set of atoms. And then any atom has neighbors that are in the same cell or in any of the, I think it's a maximum of 26 neighboring cells around about it. The second set of lattices is then used to determine which dots belonging to an atom are overlapped by a neighbor, by again putting the sphere in a set of cells. The clever thing here is that we only have to check the set of boxes that contain a neighboring atom. Both of these improve the speed of the original shrake and loop implementation by avoiding negligible distance checks. So to produce the dot surface that we use to represent our molecule, we have to take our set of atoms and generate a set of dots for each one. The clever thing in Roger's original implementation was rather than looping over all of the atoms in the molecule and for each one calculating a set of dots, we produce a standardized set of dots representing the surface of the atom for each of the possible types of atom that we could incur, done only once, and then they are reused each time we bump into one of those types of atoms, which is a little bit more efficient than doing this more times than necessary. The actual dot surface itself, so forgive me if my explanation of this is a little sketchy, is produced by superimposing an icosahedron of dots repeatedly onto the surface of the atom or sphere. The number of dots that this is produced is controlled by our depth parameter. And I've given an example of what this looks like for a protein on the left here, where the atoms are colored by type. So then getting out the values for surface area and volume is quite straightforward and is based on the number of dots representing the atom. In the case of the surface area, it is the sum over all atoms in the molecule of the radius squared multiplied by the ratio of the number of dots that are occluded by a neighboring atom and the total number of dots. The volume is given by the sum of the dot products between the radius squared multiplied by the x, y, z coordinates of the center of the atom, multiplied by the vector of dots representing the atom, the radius and the number of dots occluded by a neighbor. And then we can also get out a couple of metrics for looking at protein surfaces as well. The first, the compactness, I believe, gives the ratio of the surface area and the volume and is a measure of protein folding efficiency. And the second, the packing density, is the ratio of the van der Waals volume, which is the case where the probe radius is 0, and the total volume, and it gives a measure of the efficiency of space occupied by the protein. So to kind of look at how well this might compare to what's already in RDKit, we looked at the 2 surface area and 1 volume methods that were already available in RDKit. The first is Paul Labute's approximate surface area, which takes the sum of the value for the area as the sum of the van der Waals area of each sphere in the molecule minus the bit where 2 of the spheres overlap. It is an approximation because it only looks at cases where 2 atoms overlap. It doesn't take into account any cases where an atom has overlap with more than one neighboring atom. It is available in both Python and C++. And then the slightly more recent free solvent accessible surface area, where, because this took me ages to figure out, free simply means that it is free to use, which contains implementations of both the Shrake and Ripley and Lee and Richards algorithms. And again, it is available in both Python and C++. And then finally, the compute mole volume algorithm that's included in RDKit, which I believe from digging through the source code gives an approximation to the van der Waals volume based on putting the molecule into a grid and looking at which voxels are occupied. But this is not particularly well documented, so don't take my word on that. Yeah. And this time is available only from Python. So for the sake of a fair comparison, all of the little benchmarking studies that I'm going to show were run all in Python. and just carried out on my MacBooks. There's not any particular hardware requirements needed to do this. So the first thing that we wanted to look at was whether or not we could replicate or near replicate, given we're looking at approximations, the values that were presented in the original paper for this here, our method compared to the original algorithm in the paper and an earlier analytical calculation of surface area and volume by the same authors. And what we found was that we don't get an exact match due to slight differences in values of radii that were used and slight changes to the algorithm. But given we're looking at an approximation and an error accumulated over quite a large number of atoms, I think we get pretty close. So then we wanted to look at how well this might do over a bigger set of examples. So we took on the same subset of the Pisces database used with the original free solvent accessible surface area method, which is 88 proteins across a distribution of sizes, and that all have reasonably high resolution where all chains were included in the calculations. And we find that for our method for surface area, compared to both the Lee and Richards and Shrake and Ripley implementations in the free solvent accessible surface area, we get pretty much exact correlation between the two sets of values that we get. So pretty good match to what's already there. And again, for the volume, these correlate pretty well as well. But for the Labute approximate surface area, we get a bit of an overestimation compared to the other three, which is not unexpected given they do ignore some of the atom overlaps. So then in terms of timings, in terms of surface area, our implementation is slightly slower than what is already in RDKit, but we're quite a bit faster than the existing volume method. The caveat to that is that a lot of the hard work in calculating the double cubic lattice method is done when you call the class. So if you were looking at getting out both surface area and volume, you would be more efficient using our method. So then, given the interest, the majority of the community is more in the small molecule space, we wanted to look at how well these would compare across a set of ligands as well. So for any of you who have seen one of my talks before, you will know that PDE5 ligands are my favorite example when we're looking at shape and volume comparisons, because they occupy the same binding pocket and they're known to have similar volume and by extension surface area. And again, we find that our method compares quite well for surface area to the Lee and Richards and Shrake and Ripley. But this time the Labute approximate surface areas are quite a bit smaller. Honestly, I have absolutely no idea why that is, given we would expect them to potentially overestimate instead. And again, for the volume, we get a pretty good match to what is already there, give or take. So again, we wanted to look at a slightly larger set of molecules just to prove that this holds up. So took 47 other known inhibitors of PDE5. Appreciate these are a bit small, so you might have to take my word for it. They are quite structurally similar to each other. And again, we find that we get pretty good correlation between our surface area and the values from the Lee and Richards and Shrake and Ripley implementations from free SASA and from the compute mol volume. But again, there's a little bit of a difference between what we get from the double cubic lattice and the Labute ASA. Again, I'm not quite sure why that is. So say for small molecules, we're looking at a smaller number of atoms, so the speeds generally are quite a bit faster, and there's less of a differential between our method and what is already in the toolkit. But again, we're quite a bit faster than the compute mol volume method. So to conclude, I've presented a new method that will hopefully prove useful to the community for calculating surface area and volume using a dot surface representation of a molecule. And that compares well to the existing surface area methods and is quite a bit faster than the existing volume method within the toolkit, and also gives the option to calculate the solvent excluded volume of the protein or ligand as well. So I'm going to have to start my future work by thanking Greg for the invitation to speak today. I had originally submitted this as I'm happy to give a poster or a lightning talk, one or the other, and somehow I've ended up with 30 minutes. Because Greg had some ideas for things that we might be able to do to extend this. So one that was already on Roger and I's radar was to add in calculation of polar surface area as well, which should be relatively straightforward to do for some arbitrarily defined list of atoms that count as polar. And then Greg had suggested that there are also some quite useful 3D descriptors that we can get out of this in the form of the contribution of individual atoms to the surface area or the volume of the molecule. The list of surface points that we have generated, and then the number of surface points that are generated for each atom in the molecule. So to finish, I would like to thank my boss, Roger, for sharing the code with me and for giving permission to contribute it back to the community. The rest of the team at Nextmove, but especially John for his endless patience with my stupid questions while I was learning C++, and then to Greg as well for his help with getting the code into the RDKit and for his suggestions for future work, and yourselves for listening.
All right, we have quite a bit of time for questions.
Sorry, I appreciate I talk quite fast.
Yeah, I've got quite a few questions then.
No.
It was interesting to see that yeah, SVL seems to be faster than Roger's C++ codes, but I'm wondering what they might say to that. But I'm just wondering about to what extent when you rotate the molecule or the protein, the surface area calculation changes its values. So is it plus or minus?
Rotation of the whole thing doesn't change all too much. Change of conformer, yes, it will change.
Yeah, so rotation of the whole thing. Yeah, just wondering.
I've not tested it. I would imagine it shouldn't change.
Yeah, because it has the fixed points in a certain. And then similarly, when if you go reduce the number of points from 96 to something 20 or whatever, you can some how much, because that would speed it up. How much do you lose in the calculations?
Speeds it up. Small incrementations, the lower the number of points you go. If you were to drop it down to a depth of 1, you would lose a fair bit. So if a depth of 3 instead of 4, marginal difference.
And the last thing is, I've heard polar surface area is important. Is that something that could be easily calculated from this?
Work in progress. So I've got it working for ligand. It's a little bit more complicated to get it working for protein, but watch this space.
Thank you.
One important question, can we find Paul LeBute and give him the help he needs?
So a quick comment on the LeBute ASA, that's a 2D calculation for just so people know. So it's calculated just based upon bond increments between things. So it is not conformer sensitive. And that may explain some of the differences that we see here. So it's really intended to be an approximate measure. At some point they published that. I think the CCG had their own online journal, which unfortunately has vanished into the holes of that. It's no longer there. You can find it on a Wayback Machine. The RDKit has a citation for the paper if you care about how that's calculated. The other is, Rachel, you have 10 minutes. I mean, there could have been all of this other stuff, right?
Don't look at me.
No, I'm teasing. I do think, as I said, I mean, Noel already mentioned the polar surface area, but I do think it would be really interesting to be able to get some of this other stuff out, just because it is a super efficient method to get the atom or the points on the surface. And I think we as a community could do a lot of stuff like this. I think it'd be fun. That's not volunteering you to do more work.
That's all right, it's on my list.
Thank you. I was just wondering, and I assume that's the case, you don't need to have a fully sanitized molecule or anything for this, right? Because that's tricky to get for proteins.
Yeah.
You just need atom types, coordinates, and that's good. Nice. Thanks. And does it also work for molecules where you have fragments?
Not something we've tested.
Okay.
I can't say any reason why it wouldn't.
Yep. And so when you have a protein ligand complex, you would pass this in as a single molecule and just set the flags accordingly? Okay.
I think so, yeah. I can test it out.
Yeah, thanks.
So you can go fast. Yeah.
Nice talk. Are you thinking of mixing with partial charges for the surface? Because it's quite useful fingerprint.
Not something that we have looked at, but willing to consider it. Don't know if Roger maybe has any thoughts on this.
Yes, and it's very useful.
Maybe 2 questions, but one real quick. Have you actually tried to compile Roger's code?
Yeah, so very impressively, 25-year-old code it compiled with absolutely no complaints.
And because you made a comparison to different methods, but have you compared how, what are the results versus original code?
Exact match.
Exact match, perfect. So,
That was the first thing I did, don't worry.
and performance?
Of Roger's code.
Yeah.
It's slightly quicker than the version that matches with RDKit just because of the extra bits that go around about
Can-
it, but there's not much in it.
We can blame RDKit then. And maybe the real question would be for protein ligand complexes, can you define a boundary box?
That is not something I know off the top of my head.
Okay, I think that would be useful and probably
Mhm.
speed up the computations a bit. Thanks.
Oh, got it. No, we should do it for the people online. I need the exercise too.
That's very, very cool stuff. Naively, I would have thought to use different numbers of points for different size box or different size atoms. Why is it always 96?
So the 96 is the original implementation. I think that was just the decision that they made at the time. It needs to be relatively uniform. So I guess that extends to across the whole surface as well, rather than just the individual atoms.
Like relatively uniform per atom or relatively uniform through space?
So that's I'm saying it per atom, and I guess extending through space as well.
All right. Well, if there's no more questions, let's thank our speaker.